Yeah, we're live.
Looks like we're live.
We have liftoff. Okay, so hello, Marcello, and hello
Hey.
to everyone watching us at home. Um, I can't see how many people are there. I see a message from Lezen or Lezen. I don't know how to pronounce it. But I can see the count, Devora. Devora is in the background monitoring the chat. And we're here to talk about the Cairo Verifier. Very exciting. But first of all, maybe Marcello, you want to introduce yourself? Nice, 100 people watching.
Okay.
Did it break up? No, yeah, Marcello, introduce yourself to the audience.
Yeah. Yeah. Sorry, I got disconnected for some reason. I had to rejoin. So
Ah,
hey everyone, I'm Marcello from Herodotus. Yeah, happy to talk about the verifier today.
yeah, and I'm Raz. I'm from StarkWare, a product manager here. Been a Starker for a year and a little. And yeah, um, actually one of the more exciting projects I've had at StarkWare. And this is actually the second time we're doing something like this, Marcello and myself. Last time was just audio. This time it's also video. Who knows what we'll have next time? Okay, so I mean, I assume the first question is what is a Cairo verifier, but I actually want to start with. There's even a book that names is named as such. Start with why. Why are we even here discussing this thing called Cairo verifier? And Marcello, I'll let you start. I have my own opinion, obviously, but let's see what you have.
Sure. Of course, verifying proofs is a pretty essential piece of whatever we do, especially at Herodotus, as we generate storage proofs that allow smart contracts to access historical data and also data located elsewhere. We utilize Stark for that, Starks, and of course we need to verify them somewhere. So that's why we need this verifier. But also any other project would definitely benefit for that because as you probably know, Alfreeze can be also enabled by this verifier. A lot of other cool applications, such as, for example, client-side proving can definitely benefit from the existence of such verifier. So yeah, that's why it's useful, I guess.
Yeah, I completely agree. I want to say first, I dare you to answer the question without mentioning L3s, but no, it's obviously coupled. Although there is more than that, I think it breaks down. You can break down the question to like sub question. First of all, why do you need a verifier? And this is pretty obvious, right? We're doing zero knowledge rollups. Proofs are useless without verifying them, or meaningless, you can even say. Then you can say, why do you want, let's say, a Cairo verifier, or it's a Cairo verifier is maybe confusing terminology. What you prove are Stark proofs, so it's a Stark verifier, but it's a Stark that has the Cairo constraints and also the layouts, which we will discuss soon. So it's a Stark verifier specifically for verifying Cairo Stark proofs. And why do you need this? Because, well, Cairo is cool. We love Cairo, and specifically, it's also Turing complete, so you can prove everything. So that means you can verify everything. Um, the third question is, why do you need it on chain? And this is maybe something you usually look past, but it's worth mentioning that yeah, you have I don't know, a C++ verifier in the Stone repo, and there's also a Rust one written by Lambda class. and maybe others. But these are off-chain verifiers. Why do you need an on-chain one? Well, the same reason you need on-chain everything, right? You need something that's on a chain that you can trust, and ideally decentralized. So it's not just trust me, bro. I verified it on my computer and it works. And the last part is, why do you need it on Starknet? And this is the crucial innovation, I think, in this verifier. And there's a lot of words you can throw, like L3s and client-side proving and whatever you want. But I think it comes down to costs. Verifying proofs on Starknet is cheaper than doing it on Ethereum. I mean, it will be substantially cheaper. And with this cost reduction, this opens the door to a lot of other things. Because, I mean, and before you realize this, you can always ask, why not use the existing verifier on Ethereum that's retaining solidity? You can do app chains on Ethereum. They would be L2 and not L3. You can try doing client-side proving, but you will always hit this cost problem, which also hinders scalability and cool applications like gaming in the browser, provable gaming, and proving game execution in the browser, and verifiable machine learning, zero knowledge machine learning. So I think maybe Marcello, tell me if you think otherwise, but I think it's the TLDR, the one word is just costs.
Yeah, definitely. Like for sure, cost is important because like at the end, even if you use some applications that benefit somewhat from client-side proving, very often it may be the case that the verification cost on one completely unjustifies the use case.
Exactly.
And this is why we can benefit a lot from the same verifier being deployed on Starknet, where the verification is much cheaper thanks to the properties of Starknet. Like a good example of that, I think it's in gaming. I feel like it's still kind of an unexplored area, but for example, we could open some sort of state channels between users where they can just interact between each other, like exchange signatures, whatever, and then just prove it. And at the end, the verifier on-chain will just be convinced about the state transition, which I feel is some concept. Like state channels are, of course, like a very old concept, but coupled with like all the recent innovation in this space, we can actually see some production usage of that, and I'm super excited to see what the future will bring and what new primitives, what new things will be unlocked with this primitive.
Yeah, totally. I think Louis here in StarkWare is excited about this as well. And probably he'll have his own Twitter space or whatever this is called to talk about it, because we're not just on Twitter, right? We're on YouTube too. So I totally agree. The cost gives you speed, which gives you like proving gaming. And also customability or whatever, which is basically L3s, right? Well, we can't talk about L3s because they go hand in hand with this verifier. This is a very exciting area, but the main benefit for L3s, in my opinion, is being able to customize whatever you want. Again, you can try doing it on L2, it will just become infeasible due to the costs, or at least limit you at a very earlier stage. But as I said, I think L3s are just part of the picture because you can do a lot of other stuff that not necessarily are blockchains, so not a layer per se. For instance, verifying zero knowledge machine learning, which I think is one of the more exciting or innovation in this field. And I'm really looking forward to see how this turns out. And in general, I think this is just putting a verifier on Starknet and having it be much cheaper and open many more possibilities. And there's also one use case you demonstrated and you talked about in Denver with zero sync. You can say a few words about this. It just, I think, makes Starknet like a verification layer for everything. So right now, you can say Ethereum is this layer, and with Starknet being a layer like this, I think it enables much more. This is my take. And yeah, you want to talk, say a few words about what you did with ZeroSync?
Yeah.
Very cool example.
Yeah. So maybe let me first cover ZeroSync, and then let me add on something and comment something you said, which I really liked. So ZeroSync. So for those of you who are not familiar with ZeroSync, it's a project developed in Cairo that essentially verifies the Bitcoin consensus, like the proof of work. So basically, whoever verifies that can get convinced that, hey, this is indeed a new valid block on Bitcoin. And of course, this is written in Cairo, so whenever you run it and finally prove it, this will output you a Stark proof. But the thing is that verifying Stark proof is quite expensive, but finally with this verifier, this is possible. So effectively, you can have some smart contract on Starknet that is actually aware of what is happening on Bitcoin using this technique, which is pretty cool. Because as of today, there was like no completely trustless way to convince any smart contract anywhere on Ethereum that, hey, this is the latest valid block header on Bitcoin.
Yeah, Bitcoin on Starknet, as you famously said. And you wanted to add another comment?
I think. Oh yeah. So I really like what you said about layer 3 being like this place where you can write your logic in a very specific manner, tailored for a use case. I think there is something more deep to it. Is that I like to think of blockchains like this global state machine, right? But this global state machine, like, why would the validator care that I made some action? Like, I probably don't want the entire world to know that. Like, if you're like building a game, we just care about the participants of the game being assured that, hey, everything that is happening inside is valid. And then at the end, we just want to settle this information somewhere. And I feel like the separation of concerns powered by Starks is actually great. I'm going to see a lot of innovation, and super happy that we can contribute to that with the verifier.
Me too. Okay, so we covered the why. I think I hope people at home agree that we made a persuasive case. Now maybe let's say what is the verifier. I think this will be the shorter part. Marcello and I are both not marketing guys, so I think we're both interested in like the technical stuff, which we will deep dive very soon. But first, let's just make things straight and say what is a verifier, a Cairo verifier. Mm-hmm. So Marcello, go ahead. Or maybe let me try and correct me, because you're far more familiar in this than I am. So basically, we're talking about the Starknet contract, right? Just one or maybe two? Is it just
as of now it's one contract, but we're still improving some stuff, and it is a possibility that it will be many contracts.
No, yeah, okay, but now it's just the one, including
right now it's no
fact registry, right?
Yes.
So yeah, it's just a contract on Starknet, a singleton that gets a proof generated by Stone, a Stark proof generated by Stone over Cairo program, and verifies it, means checks that the proof actually proves the execution of this program. If not, it rejects it. And if it is, it registers what is called a fact, attesting to the validity of this execution of this proof on a component usually called the fact registry. Then it can be queried to actually assert that this proof was verified, so it's correct. and continue with whatever logic you want. The most well-known, I think, use case is updating the state of a blockchain according to the fact register that the transition was indeed correct. But again, you can do much more. You can, for example, verify the Bitcoin chain. You can also verify zero knowledge machine learning. You can also do what you guys do at Herodotus, which maybe you can say also a few words about this. But do you agree with my quick summary?
Yeah, I will put my best efforts to ensure that this is indeed the shortest part of this Twitter space. So, what is a verifier? Oh, that's quite of a philosophical question. Like, I guess first we should probably iterate what Stark is and what Cairo is really about. So let me speed run this as much as I can. So Cairo is basically an architecture, like a virtual machine as well. And this comes with a constraint system that can be satisfied and proven with like Starks. But of course, as you mentioned before, proofs are useless if we don't have a verifier. And the verifier is basically a set of like operations, some logic that needs to be executed in order to actually verify this proof and be convinced that this proof attests to what has been proven. So now to be more practical, we developed this verifier as a smart contract on Starknet, such that on Starknet we have some logic that is able to get convinced that, hey, someone indeed properly executed this Cairo code. And this is implemented, as you said, in this model of like having a fact registry. So what is a fact registry? A fact registry is basically some abstraction on top of the idea that, if we verify just some Cairo code, it doesn't mean anything. We want to verify some very specific Cairo code. And also we want to verify that this very specific Cairo program, given these inputs, return these outputs. And the fact registry is basically like an abstraction that makes this process kind of developer friendly and understandable.
Yeah, your answer was much better than mine. Thank you. Cool. Anything you want to add to this part?
Yeah, maybe just for some context, why this is also useful for Herodotus. For those of you who don't know, at Herodotus we allow smart contracts to access historical data as well as data located in other places on Ethereum. And one of the tricks we use to make this possible is something that we call generating and updating the historical block hash accumulator. So basically, the idea is that we convince some smart contract that indeed there is a commitment to all of the block headers that ever appeared on Ethereum, and we need to basically prove the state transition. And thanks to the fact that we now have a chip verifier that is available on Starknet, we can do this with a higher frequency, so which implies that we have lower latency.
Yeah, and if you want to learn more, please, I encourage you to do so. And you can also listen to the last time Marcello and I talked, but only hear us, not see us. Okay, I think we're good to go and move to the actually interesting part of this talk, which is how did you manage to do it? And I have, it was quite a ride, right? We've been at it for I think a little over 3 months now, right? Yeah, and it was definitely an interesting road, not without challenges and difficulties. And there are some that I wanted to talk about specifically. I think it highlights many interesting choices you made and challenges you overcome. So let's start with that, and let's start with the basic, because we say the Cairo Verifier. It's actually a confusing name. It's a Cairo verifier written in Cairo. So it's a Cairo verifier. Right? It is both written in Cairo and proves Cairo. Cairo is the most overloaded term, I think, in our space. And I wanna. So we kind of explained why it needs to prove, why it should prove Cairo, and also why it should be on chain on Starknet. But to be on Starknet, you don't necessarily need to be written. There are two options, right? Because there are two Cairos. There is Cairo 0, the old Cairo, and there's the Cairo 1, which we just call Cairo now, which is the newer version. And I don't know how many people know, but there is already a Cairo 0 Cairo verifier, which is part of the Cairo Lang repo. So the question arises, and your Cairo verifier, maybe we haven't mentioned, is written in Cairo 1. This is the so the question arises, why? I mean, why not just take the Cairo 0 existing verifier and use this on Starknet?
Okay, so first of all, thanks for this Cairo introduction. It's super useful. So maybe for some context, the verifier written in Cairo 0 is actually very useful for recursion and was a great reference for us. So now how this verifier is built. So as Rod mentioned, it's implemented in Cairo 1, but what's important is that this verifier is designed to function as a smart contract deployed on Starknet, whereas the Cairo 0 verifier in the Cairo Lang repo, like I mentioned, is used specifically for recursion. Yeah, so now how we have achieved that. So we of course had to operate within some constraints imposed by Starknet itself, because of course depending on where you do the computation, you're gonna have different trade-offs. So we had to adjust to these trade-offs. So why we decided to do it in Cairo 1, first of all. So it is possible to deploy Cairo 0 on Starknet. Still, it's possible, but soon I don't think it's going to be a possibility. Ross, you tell me. I think it's going to change like in a few weeks, right?
That's true. Yeah.
It won't be.
It won't be possible soon. I can't commit to the exact time, but yeah, this is like the technical detail. But assuming that you will be able, I mean, if you deployed it right now, it would be okay and it would live forever, assuming you don't want to abrogate it. But I think that this is the more technical reason, and there is a more, in-depth answer to this question.
Yeah. So first off, like this verifier written in Cairo 0 would require like a significant refactor to operate within this the constraints of Starknet, and also like Cairo 1 is pretty flexible, which means that whenever there will be some upgrades to the overall Stark protocol used specifically for this Cairo interaction, it will be much easier to handle that in Cairo 1. A good example of that is just switching the hash function. In Cairo 1, that was pretty straightforward. And literally every week we experiment with different setups. Whereas in Cairo 0, that would be quite painful, as abstractions are quite costly.
Yeah, I think it's just, I mean, I can say that it's not a trivial question, right? We talked and debated whether to do it in the Cairo 0 or Cairo 1. But ultimately, Cairo 1 is just a much better language. And yeah, it's much more flexible and it's easy to make changes like the hash function changes you did, which we'll discuss soon. And yeah, I think ultimately this was the right call and the right way to go. Just yeah, for people at home, use Cairo 1. Also, no, it's just Cairo. If not for the reason that it's probably you won't be able to deploy Cairo 0 contracts on Starknet in the near future. Okay, and maybe you mentioned it, so I'll add a bit on why there is this Cairo zero verifier. Anyway, so it's used in the sharp, in the StarkWare's prover, in the recursive proving mechanism. So we use the Cairo verifier, and this verifier is written in Cairo 0 because it was written quite a while ago. And there is actually a good chance the Cairo 0 verifier will be rewritten in Cairo 1. Again, because Cairo 1 is just a much better language. Okay, maybe, yeah, this is, I think, I was just interested, how was the experience for you to write in Cairo 1 in this a project of this size?
That's actually a great question. So Cairo 1 is still like an evolving language. So the nice thing is that we keep seeing like new features that actually significantly improve not only the performance of this verifier, but also the overall developer experience. So it's quite nice that we can have some influence of where the language is going, and also the tooling. But like I mentioned, overall the experience has been great because Cairo 1 is just a way more flexible language than Cairo 0. There are also like many verifiers written in Rust, and Cairo 1 is in some way mimics Rust. So that was also very, very helpful. The ability to, kind of use the same patterns, so that this code is very readable to other developers. Because like in our opinion, what really matters about the verifier is like the auditability, how many people can actually understand what's happening. Because this verifier is something that you have to put trust in it. And if it's not auditable and it's written in a language that is very hard to reason about, that's a bad thing.
Yeah, that's actually a great point. It's not your everyday program or contract. This is one you really need to working properly. And we know that we audited our Cairo 0 verifier, and it was no easy task. It required experts in crypto. And the readability of this is definitely very important. I completely agree with that. And yeah, I think exactly as you said. I think I asked you this the last time we talked too, because you wrote Cairo code also for Herodotus, but I think this was far bigger magnitude, and it even it demonstrated even more how you can affect things in the language. Just this morning, I think we got a request from you for one of the features, and it's not without challenges. You mentioned tooling. Some, as you know too well, are still lacking in Cairo 1. But I think we overcome this obstacle as well. And actually, I can say this is specifically, I'm talking about profiling tooling, which you use to keep profiling and benchmarking the verifier, and they actually progressed while you developed. So it was both challenging, but it was nice to see the progress go hand in hand. Okay. Moving on, unless you have anything to add on this.
Let's move on.
So we talked about comparing the Cairo, your verifier, which is Cairo 1, to the Cairo 0 verifier. I thought it'd be interested also to compare to the Solidity verifier on Ethereum. Because again, there is one, otherwise we won't be able to verify, for instance, Starknet's proof and state updates. And these are completely different languages, and also different chains. And I thought it's worthwhile talking about the difference, and specifically one big difference I thought is interesting is that the Solidity verifier on Ethereum is by no means one contract. It's I can't remember the exact number. I think I counted one, and it's more like it's a couple of dozens, I think. And yeah, that's something not everyone knows. And yours is just one. So maybe say how come and why you did it. Yeah.
Okay, so this will move me to my previous point. We really believe that the verifier is something that you have to trust, that should be auditable. And when something is part like across many contracts, it's very hard to reason about it. And this is not something we really wanted to avoid in this design, because not only it affects the overall perception and the amount of trust people will be able to put in this code, but also the speed we can move with. Because of course, like when everyone in the team is able to work with this and the architecture is relatively simple, everything moves faster. So this is why we decided to go for a monolith. But maybe to defend a little bit the solidity verifier, like one of the reasons why it's done in this way or not another is because solidity and the EVM imposes significant constraints. Such as, for example, there is a limit on the amount of cold data you can pass, amount of computation you can do in one Ethereum transaction. And of course, like verifying a Stark is not trivial, which means that the proof very often needs to be split into multiple parts on EVM. Whereas on Starknet, we don't have the same constraints. We have different type of constraints, which allowed us to take this decision to go for a monolith.
Yeah, thank you for pointing this out. Obviously, we're not doing stuff for no reason here and stuff. We're not splitting logic just for the heck of it. Yeah, exactly as Marcello said. Ethereum poses restrictions and limitations, and that's why we decided to split the logic to be able to meet those limitations. And exactly as you said, Starknet has little less limitations or other limitations. It's also more flexible, and I think this is also part of the collaborations and the impact you've had. We throughout this work, we understood what limitations are actually necessary, which can be relaxed, and we're still working on it. Right, this is specifically one challenge we're still working on overcoming, but it's much. I think it's way more flexible and doing stuff on Ethereum. And as always, doing stuff simple is always better. So if you can, definitely. Okay, and so maybe I'll jump to a question I wanted to, or a topic I wanted to discuss later on, but it relates to the limitations you've mentioned, which is the mysterious bootloader program. I think some people know this, most not completely unaware. And it's kind of a mythological creature that very few people understand truly. And I think in this work, you come to be very familiar with it. So I think it's worthwhile using this platform to talk about it too, and how. What is this thing? Why does it exist? How it relates to the limitations on both Ethereum and Starknet, and
Sure. So let me take a huge step back and let's talk about one properties of zero knowledge. So one very cool thing is that in this type of protocols, the verifier doesn't need to see everything, which is amazing because it enables use cases such as ZK rollups. Because I don't need to see every single transaction to be convinced that this is indeed the new state and the state is valid. However, I still need to see something. For example, the previous state root, and some commitment to the transactions that have been executed. And of course, the same is for verifiers, and specifically in Cairo is the same for programs in general. So the verifier, of course, needs to see what is being executed, because like, why would you verify the execution of something if you don't know what's being executed, right? But this can be tricky, because a program can be quite big. An example program that is pretty significant is, for example, Starknet itself, like the Starknet OS. And imagine that every time you would verify proof that transitions the state of Starknet from one state to another, you need to load the entire bytecode responsible for this logic. That would be pretty bad, because it's just a long bytecode, right? And this is something that needs to be visible to the verifier. So in that case, in the case of Starknet, to the L1 verifier. So that's pretty tricky, but thankfully there is a way to overcome this, and these are bootloaders. So now, what is a bootloader? Basically, it's a program written in Cairo that, as a public input, takes public input is an input visible to the verifier. Takes as a public input the hash of the program, so we don't have to reveal the entire program. And simply, as a private input, would take the actual bytecode, execute it, and say, hey, here I'm proving to you that I executed this properly, and this hash actually corresponds to the executed bytecode.
I think I just thumb up down you, but I actually meant to thumb up. I don't know what happened. At least I saw it on my screen. I don't know if people did you see it? The bubble with
I could see that.
Or I
anyways,
don't know.
just to.
But yeah, I interrupted you. Go ahead.
Just to add like one more sentence to that, with the trick of using a bootloader, we can significantly reduce the verifier complexity, because a verifier doesn't have to see the entire bytecode, and this is what the bootloader enables.
Yeah, exactly. So the claim changes to I ran this program, which I ran a program which hashes to this hash, and got these outputs, right? Instead of I ran a bootloader that ran this program with this that hashes to this hash and had these outputs. It's maybe it doesn't go well verbally, but I hope people at home got it. And this is how we do it for the Ethereum, for the Solidity verifier on Ethereum as well. And yeah, just this morning we discussed about the option of hard coding the code of the bootloader and not passing it as call data as well, to even further reduce the size of the call data that you need to send to the verifier, because this is the major factor that it affects, right? The call data size. And yeah, let's see what we decide. Actually, Marcello just just before we went live, tried to explain to me another trick he found. I don't know if maybe we will save this for last. No, you know what? I'm interested. You want to explain this now?
Okay, sure. So there is a limitation on Starknet. So actually, one transaction can upload up to 4,000 files in one transaction. Of course, Stark proofs are quite big, and especially if the executed program is big, aka it means that the verifier needs to be aware of what the program is. It's going to be a problem. But we use bootloaders, perfect. But the thing is that every time we verify the proof, we need to upload the bytecode of the bootloader to the verifier, which is quite redundant. However, we thought of actually finding a better trick, because part of the public memory is also the output of the program. So even if we put the code of the bootloader into the smart contract, you don't have to re-upload it, but we have a lot of inputs and a lot of outputs of this program, it's going to be an issue. So we thought, okay, how do we make the proof smaller? But if we cannot make it smaller, how do we overcome this limitation of 4,000 files? And actually, we came up with an idea of just taking the proof and basically converting the proof into Cairo code, however that sounds. So the idea is to take the proof, split it into, for example, 3 parts, deploy these 3 parts as just some stupid hard-coded files, on Starknet. And what is important, bytecode deployed on Starknet does not get committed to layer 1, so there is no stake diff. Yeah, and basically that way, what we can do, we can just call a contract on Starknet that has part of this proof that we call again and again, and basically we don't even need to upload the proof in the call data because we upload the proof as bytecode. So it's kind of a dirty trick. It's kind of gaming the sequencer, but probably it would work.
Yeah. If that was too technical for people listening at home, then it's okay. If you understood it, then hit Marcello up afterwards and also explain it to me. No, Marcello will talk about it. We'll see if that actually works or if we think it's gaming the system too much and just block it. Let's see. But moving on, maybe that was a bit too technical. Another limitation I wanted to talk about, I mean, we talked about the call data. This is one major factor limiting the verifier and how you develop and design its architecture. The other is obviously how many steps does it take for verification. And one thing we probably knew before, but understood all too well during the work on this Cairo Verifier is the importance of hash functions. So, Marcello, you want to, say some words about this, describe your somewhat painful experience with hash functions in the verifier?
Sure. So maybe to give some context first, I like to categorize hash functions in two ways, especially in the context of like working with ZK. There are ZK-friendly hash functions and CPU-friendly hash functions. So CPU-friendly hash functions are the one that we use all across the web and let's say in the normal world, such as, for example, SHA, like MD5, Blake, Ketchuk as well. That is used a lot in Ethereum. And then we have other types of hash functions that are mostly related to ZK, such as, let's say, Pedersen, Poseidon, Rescue, and so on. Specifically in the verifier, we can, and also in the overall Stack protocol, we can use a combination of both, because the, let's say, CPU friendly are also called prover friendly, whereas the CPU unfriendly, which are at the same time verifier friendly, they can also be used in the protocol. And basically, the reason why we have these two options is because we can kind of play with the trade-off and find a sweet spot between the prover and the verifier when it comes to verification cost and proving cost. So now for even more context, Poseidon is actually very good for the verifier because it's easily arithmetizable, so it just doesn't cost a lot on Starknet. That's a basic explanation. But on the other side, it's quite expensive for the prover. So in the past, we tried with proofs that just use Blake 2s, which is super friendly for the prover. But the thing is that it's extremely expensive for the verifier. And one of the main factors that affect the verification cost is indeed the hashing function.
Mm-hmm. Yeah, extremely inexpensive is very accurate. But Poseidon is apparently, I mean, not apparently, it's not surprising. It's a great hash function, especially for verification, also for proving, and that actually, I mean, that was also an interesting part of this collaboration because, I mean, first of all, I should say this is a configuration of the Stone prover. I don't know how many other provers let you play with the hash function the same way Stone does. Using this extended, Stone actually used Poseidon before, but it extended the usage of it in the protocol, in the proof, and as such in the verification. And that's something that we've been working on. I think it started before we started working on the verifier, and it takes time, but throughout this the work and this collaboration, it really pushed things to production. So it ended up being out sooner than we thought, and it was like a very, I think, a nice demonstration of the impact you've had on us, basically. Yeah. Okay. I think one last thing I had in mind is talking about layouts again for the interest. And I know you talked about it in Denver too. Marcello was just in East Denver, which where he gave a talk about the verifier as well. I wasn't there, unfortunately, but I hear it was great. And I know you also use this opportunity to again demystify and maybe clear things out about layouts, because again, not many people know what this actually is and how they play out in this setting. So yeah, I thought it's worthwhile also talking about it here, and yeah, how it affected the work on the verifier.
Sure. So maybe let's introduce what layouts are. So layouts are effectively a combination, a set of so-called built-ins. Another word, what are built-ins? So Cairo is an architecture that allows you to run some computation and express whatever you can as it's Turing complete. However, certain operations are just very expensive. For example, hash functions such as catch-up. And there is a solution to this problem, and the solution is called built-ins. You can think of built-ins as some sort of sidecar to the main CPU that are just responsible for a very specific operation and are optimized specifically for that operation. So that's basically a built-in. But the thing is that when you take the CPU and then all of its sidecars, it's going to change the way how you arithmetize the whole thing, which of course affects both the prover and the verifier. Yeah, and now how does it affect the overall thing? Well, the less built-ins you use, aka the simpler layout, the cheaper is the verification, and also most importantly the proving. Yeah, and what type of built-ins do we have available? For sure, Pedersen. For sure, we have Poseidon. We have also already mentioned Ketchak, bitwise built-in, rain check, output pointer, output built-in. Not sure if this should be actually classified as a built-in, but
yeah,
it's
yeah,
it is a built-in. And then I think there is this new one, like range check 96, something like that.
correct. But this, let's put it aside for now.
Okay.
It's on a hush hush. No, just kidding. So yeah, I hope that cleared things out. And yeah, maybe should mention the work so far was on a layout called the recursive layout, because this is the one used for the recursion. Not surprisingly, which is what, as I mentioned, the Cairo Zero verifier is used here. But there are other layouts, and the Cairo verifier on Starknet is expected to support all layouts. There are some that are more tricky than others, right? There are ones that are basically bigger than others. There are more constraints. Not surprisingly, the ones that include the catch-up built-in, which is the most complicated built-in. I think it's bigger than all the other built-ins combined.
Yep.
And we're trying to solve this issue also these in these last few days. We have a question from the audience, but I'm not sure I fully understand it. Marcello, maybe you do. It says at what overhead is the proof generation of the program currently running? Oh, I see, by Diego. I don't know how to pronounce the last name. I'm not sure I understand the question though. Marcello, do you?
I guess it's related to what is the overhead for the prover to prove something. So it depends for sure on the chosen layout. It also depends on the amount of steps. So maybe why on the layout, as we're talking about the layouts. So like I mentioned, the layout affects the error. And for those of you who ever try to get deeper into Starks, there is something called composition polynomial. And when you do the verification, you have to evaluate a few points over this polynomial. And on the prover, well, you have to do FFTs. So the less complicated this polynomial, then the faster the proving. But also you have the number of steps, which is quite significant. And finally, we already spoke about it, is the hash function. Because if you go for something that is verifier friendly but prover unfriendly, the overhead is going to be significant.
Yeah, we played around with it quite a bit. So Diego, I hope that answered your question. If not, maybe ask again. I think the answer was that there is no answer. Right? There is no one answer. It depends on multiple factors, as Marcello says. Okay, let's see if I forgot anything. We talked about Cairo, or in its full name, Cairo 1 versus Cairo 0, and this monolith architecture versus Solidity, the Solidity verifier's split architecture. We also we skipped to talking about bootloaders, and why, well, you should maybe verify only bootloader proofs. I don't know what people at home think. We covered hash functions. I didn't ask you which hash function is the best in your view. I don't know if it's a fair question. Do you have a favorite hash function?
I think it's an unfair question because it again depends on what we're optimizing for. But if we care about the verifier, I guess Poseidon is the best.
Yeah, it's an unfair question. I think Poseidon was really surprisingly pleasantly surprised.
Also, Poseidon seems to become a standard in the industry to the point where people are even harder accelerating that specific hash function, which means that it might become friendly for the prover as well, maybe in the near future.
Mm-hmm. Okay, so we're getting the red light, I think. In stand-ups where you have a flickering light that shows that you need to wrap things out. There's no light here, just Dvora messaging us in the internal channel. So let's wrap it up. Are there any I don't know, other stuff you want to mention that we haven't, or just general you want to address?
Yeah, I think that in practical terms, this verifier doesn't really care whether we verify Cairo 0 or Cairo 1. It's mostly a question of like the tooling and what Stone is able to do. In the near future, it's going to be able to do both Cairo 1 and also Cairo 0. As of today, from our experience, we saw that working with Cairo 0 is still easier. However, Cairo 1 is also can also be proven.
Yeah, that's something we're working on right now, and it's expected, I think, very soon. Yeah, maybe worth mentioning that Cairo 0 has its advantages. Namely, it can be more efficient in some scenarios. But yeah, definitely. Let's see. Yeah, if people are, first of all, I can end with saying that I'm personally very excited about this and seeing this to its very forgot how to say it in English, but seeing it to the end, which is it's coming to its end pretty soon. I mean, it will continue to evolve and upgrade it, but I think this stretch is coming to its end. And for me, it's exciting and a bit sad actually too. But yeah, for people who are listening to this and are Cairo Verifier appealed, do you what should they do? Do you have any suggestions?
Please go check our GitHub. Also join the relevant Telegram chats and feel free to reach out. Always happy to help, and especially hear what type of ideas you guys have to utilize this verifier.
Yeah, completely agree. I encourage you all to do so. And with that, I think we'll wrap things up. So I want to thank you, Marcello, for coming to this talk and for all the work that you've done, you and your team, and Herodotus, the team at Herodotus on the verifier. As I said, it's far from over. It's just this part is. And yeah, I mean, it's already maybe we haven't mentioned, but there's already a contract deployed on testnet to be deployed on mainnet very soon. And yeah, so thank you for that and for this. And thank you, Devora, for monitoring the chat. I think we don't have any more questions. So yeah, I think that's a wrap.